Hi, everybody. This session is going to be focusing on how we can display data that we've collected, how we can describe those data, and how we can generate what we call indices of relative standing, which tell us about where particular score values stood in relation to other scores in the group. This material that we're covering in this session corresponds to section 2 of the class notes that I've given you. And I'd recommend that you have a read of those class notes as well, because they go into a bit more detail than I can in this brief video. Okay, so these steps that we're talking about basically take place when we've reached the joyous point where we finish collecting our data. So it's always an exciting, bit of the process, bit of the research process. And so usually the first thing that we want to do is to display these data, organize and display these data in some way that, allow us to easily see broad attributes or broad characteristics of the kinds of responses that we got. Now, the most common approach to displaying data is what we call a frequency distribution. So a frequency distribution can either be shown in tabular form, like in a table form, or in a graphical form, like as in a frequency histogram or frequency polygon, which we're going to be going on to in a minute. Most typically, it's in a graphical form because, people like me prefer to look at pretty pictures than tables, generally speaking. And generally speaking, also, when I have a more complex sort of, set of data, as in we can have many different score values. A frequency histogram or frequency polygon, that is a graph of the data, going to be a bit more easy for me to actually see patterns in than a table. But if you have a very simple sort of, distribution, you can actually use a table, and that can be just as good as looking at, at a graph in some cases. So the example that I've given you here is a table, obviously, and I've used the example that I gave you in the class notes of the survey that I sent out to master students about whether they loved or hated my statistics classes. So a 1 represents hate for the classes, a 5 represents love. So as you can see in the first column of my table there, all I've done is that I've got my score values on the left, 1, 2, 3, 4, or 5. So there are only 5 possible score values in that questionnaire. And I've put the frequency of responses to each of those score values in the first column there. So you can see there that only one person actually put a score of 1 and said that they hated my statistics class. Hopefully somebody who went to the wrong side when they were filling out the questionnaire and, thought that was actually the love side of it. Fingers crossed. And so that person is the only person who actually gave a score value of 1. Nobody put 2, nobody put 3. 6 people put a score of 4 or a value of 4 or responded with a value of 4. And 13 people gave a score of 5, which indicated they, of course, love my statistics classes. So we have one score value there that seems to be quite different from all the other score values in our group. In the third column that in the table, I've computed what can sometimes be a useful indicator, which is what we call cumulative frequency. And the cumulative frequency basically just expresses how many score values fell up to a certain point, up to a certain score value within my set. So as you can see, from 1 to 3, we had only 1 response, within that score range. At the point of 4, at the score value of 4, we had 7 responses. And at the score value of 5, obviously, we have all 20 responses recorded by then. The relative cumulative frequency can also be quite a useful interpretive tool sometimes. And this is basically a direct translation of the cumulative frequency in the previous column. So to get a relative cumulative frequency, I basically get a percentage instead of expressing it as just, a number, percentage of the entire sample who scored up to a certain point in our score value range. So as you can see, only 10% of the people in the group responded with, between the ranges of 1 and 3, right? 10%, 10%, 10%. Then at the score value of 4, we jumped to 35% who had already responded by then, and then up to 100, obviously, by the time we hit the score value of 5. So, you can see here that in a simple situation, a frequency table can tell you a fair bit. Obviously, we have, a bunch of scores here, which are very much grouped around the top end of the score value range that we have, and just one what we call outlying score there, which is the person who put a 1 saying that they hated my statistics classes, Again, must have been a mistake of some kind. Okay, so the alternative is to use what we call a frequency histogram, which is a graphical representation of exactly the same information that I had in my frequency table as presented earlier on. So with a frequency histogram, we represent frequencies of, particular score values, or the frequencies with which we recorded particular score values in our group using bars. Basically, that's, what a histogram is. So once again, we're representing exactly the same information here as in the frequency table. We basically plot the score values that we've got along what we call the x-axis, which is the horizontal axis of our graph. And we plot the frequencies with which, or by which those score values were recorded along the y-axis or the vertical axis in our graph. So now you can actually see here that this particular diagram or particular graph is clearly not of the same data that we used in the previous example, because that was quite an unrealistic distribution or group of scores that we were talking about there. I've just taken a hypothetical bunch of scores here to generate this frequency graph or histogram that we're looking at right there. So you can see that in this graph, basically, we actually have a distribution or a shape that is actually quite, reminiscent of the bell-shaped curve, basically. So we have a lot of scores bunched at the central point of the scale, of the score value scale there. Okay, so most of the score value, most of the responses that we got are actually sort of around the midpoint of our score value range. And then the frequencies taper off as we get more and more extreme in terms of our score value range. So that is actually what we call a bell-shaped distribution, or reminiscent of that. It's never going to be exactly the same as a bell-shaped curve or a normal distribution if we're dealing with real data, but that is fairly bell-shaped, the one that we're looking at there. A frequency polygon actually contains exactly the same information once again as a histogram, except that we use lines instead of bars to represent where the frequencies actually fell in our group of scores. So in order to do a frequency polygon, we basically take the midpoints of the bars that we can see in the frequency histogram, and we basically put points that, in the middle of each of the bars, and then we actually draw lines in between them. Frequency polygons are, less easy to interpret, I would say, than frequency histograms, but they can be quite useful if you want to compare different distributions to one another. Okay, so, but basically these all contain pretty much the same information. The idea is really to represent how frequently each of the score values was recorded in the data that you actually collected. Okay, so these are the most typical sort of displays that we do. So once we've actually got those graphical representations of where all the scores stood in terms of our score value range in our measures, we can now start thinking about the shape of the distribution that we have. All right, so now we already talked about the normal distribution here, which in the previous slide, which is basically reminiscent of a bell, right? So basically we have a lot of scores clustered around the midpoint, right, the middle of our score value range, and then they taper off, right? They taper out as we get more and more extreme in terms of score values. So now when we talk about the symmetry of a frequency distribution or a frequency graph, what we're talking about is the attribute known as skewness of the distribution. So the skewness refers to whether or not your distribution of scores, the frequency distribution of scores that you've got there, is either normal in form, like bell-shaped, basically, which is, reminiscent of the normal distribution, or whether or not it's more bunched up to the left or to the right. That's the skewness of the distribution that we're talking about there. Now, that's quite an important consideration if we want to run certain types of stats on our data, which we'll get to later on. But one of the assumptions of many of the tests that we want to do in quantitative analysis is that our data are normally distributed. Right. In other words, that the shape of the distribution that we've got with the data actually represents a bell, right, or a normal distribution, and isn't sort of bunched up on one side or the other, or flat or peaked, right? So one of the assumptions is generally that we want our data to be looking like a bell-shaped curve. So as we can see in the diagrams that we've got, or the pictures that I put in the PowerPoint there, the middle one, right? In terms of the skewness, the middle one there indicates no skew. That is that basically we have a symmetrical distribution whereby, you know, the two sides of the central tendency point, which is the mean, median, and mode, those two sides are more or less mirror images of one another. It's a symmetrical distribution. On the left, in the graph on the left, though, we can see that what we have is a negatively skewed distribution in which all of our scores are bunched up on the right-hand side of our score value range, and we only have a small number of scores, you know, toward the left side of our score range, which basically means that it's a negatively skewed distribution. You know, the negative skew indicates that the score values, right, that the lower frequencies are attached to the lower end, right, of the score value range. And this is the situation that we had when we talked about, you know, people loving or hating my statistics classes. So basically, most of the scores in that situation were bunched up on the right-hand side, which is loving the classes. And then we had, you know, just one, right, that dragged out, you know, the distribution that we had to the left, which is somebody who basically said that I hated the classes, but hopefully was making a mistake in doing so. So now we can see that if we have a negatively skewed distribution, we get that drag of the distribution out to the left, and we've got the bunching to the right. If we have a positively skewed distribution, it's basically the mirror image of that. So a positively skewed distribution has most of the scores bunched up on the left-hand side, or, you know, the lower end of our scale, you know, our score value range. And then we just have a few high scorers that are dragging out the distribution to the right rather than to the left in this case. So one of the interesting observations that I'm going to point out to you here is that our three indices of what we call central tendency, which we're going to talk about in a little bit, the mean, the median, the mode. If we actually have a nice bell-shaped distribution, the mean, the median, and the mode, as long as it's a perfect bell shape, are going to be at the same point. They're going to fall at exactly the same point. If it's, you know, largely bell-shaped, but it's not totally perfect, they're going to be around about the same sort of point, the mean, the median, the mode. If we have a negatively skewed distribution, we're going to see that the mean is actually lower than the median and the mode, because the mean actually takes into account the values of the scores themselves, right? Whereas the median and the mode don't. So what that actually means is that if you've got some very low scoring people, right, a few very low scoring people in your distribution, but the rest of them are all bunched up, you know, on the higher side of your score value range, the mean is going to get dragged down because of those extreme scorers that you have, you know, who are at the low end of your score value range. So those extreme low scorers are going to drag the mean down with them. And as a result of that, the mean is going to be lower than the median or the mode, which don't take score values into account. Alternatively, you can, if you've got a positively skewed distribution, your mean's going to get dragged up, right? Because again, the mean takes into account the actual score values, and therefore the mean is going to get dragged up with those extreme positive scorers that you have in your distribution. Let's take it as one example of income levels in Australia. Now we know that the vast majority of us are kind of, sort of hovering around that kind of lower end of, of the potential, sort of annual income levels that are possible within Australia. And then we've got some people who are right at the top, right? They're earning much, much more money than anybody else. So that is actually going to be, income levels in Australia are likely to be a bit positively skewed, although there's going to be, also some very low scoring people in there. But the vast majority of us are going to be packed around a certain sort of central point. But then there are going to be people who earn obscene high amounts of money, and they're going to actually create a tail that drags to the right. So it's likely to be a positively skewed distribution we're looking at. So let's just think about it for a second. If we actually take the mean income level, that mean is going to actually take into account those very high income levels. And as a result of that, the mean is going to be carried with those high income levels and actually get dragged up, right, as a result of that. So that's an interesting point to note for a little bit later on, that, you know, in such cases, when we actually do think that there are going to be some scores there that are going to have too much of an impact on the average that we have, we might want to consider using, you know, a different indicator of what is a typical score in that distribution, because we might think that that creates a misrepresentation of what a typical score is in that group. Okay, moving on now to the flatness or peakness of your distribution. This is an attribute or a characteristic known as the kurtosis of the distribution. Now, I've given 3 examples to the right, once again on your PowerPoint. If you have a mesocurtic curve or distribution, what that means is that basically it's nice normal curve, and therefore basically you have nothing to worry about. Your distribution is reminiscent of that, you know, of a normally distributed sort of variable, bell-shaped, basically, perfectly bell-shaped. If you have what we call a leptokurtic curve or distribution, what this basically means is that it's peaked, right? It's peaked. So if you have a peaked distribution like the one in the picture on the PowerPoint, what that basically means is that you've got a central point, right? You've got a central you know, sort of point for your distribution. And then the other scores in the distribution are very tightly packed around that central point in your distribution. That creates a peaked curve. So essentially in that case, you've got a central sort of tendency point, which is your mean, median, or mode. And then the other scores actually don't vary that much around that so-called typical score or central tendency point. I'll be getting to those terms in a little bit as well. If you have a platykurtic curve, what you see here is a flat curve, right? So instead of the leptokurtic curve, which is actually a peaked curve, you now have a flat distribution of scores in which basically you might have a central tendency point right in the middle of that curve. But in actual fact, the platykurtic curve indicates that the other score values in the group were actually very spread out around that so-called central tendency point, or, you know, mean, median, and mode that you've got in your distribution. So with a flat curve, you've got a lot more spread, right, around of people around that central tendency point that you have. Okay, so the next step after we've you know, talked about displaying the data that we have is to now think about ways in which we can describe, you know, the group of scores that we do have. So there are 2 indices that we're going to be using in order to achieve this goal. The first is central tendency, the second is dispersion. So first of all, I'll talk about central tendency. Now, I've already used this term, you know, up to this point, because it's basically part of my vocabulary now, but you might have to go back and re-watch some of that, you know, after we've already defined what that thing is. Okay, so when we talk about central tendency, what we actually mean is basically like, you know, the notion of a typical score within a group of scores. So central tendency, is there a central point in the distribution that actually houses most of the scores in the distribution, right? So central tendency means, is there actually one or more points where the scores tended to cluster, the frequency of scores tended to cluster within the group? So the most common, you know, measure of central tendency is probably one that you're very familiar with, which is the mean. The mean is basically the arithmetic average of the scores that you have. And that's, as I said, it's the most commonly measured, commonly used measure in, you know, reported statistics, as well as in the kind of statistics that you're going to be doing in this unit. So in order to get the mean, I use that formula that I've got showing on the PowerPoint, in which I basically use the summation sign indicating add them up, right? So in your class notes, I said basically the summation sign, it means just add up with whatever is you know, in front of that. So from that formula, we basically take all of the scores that we've got in our group, add them up, and then we divide by the number of scores that we have to get an arithmetic average. So that's the most typical, you know, indicator of what is a typical score within a particular group of scores. Even though it's the most common measure, as I've talked about earlier on, the mean actually may not be your best indicator of what a typical score is in a group of scores. This can be particularly true when we're dealing with a distribution, a group of scores, right? Group of scores in which there's a positive skew or a negative skew. That is, the scores are all bunched up on one side of the score value range or another. And as we talked about in the last slide, basically, this can have, using the mean in that case can actually result in you either getting an indicator of a typical score that is too high or too low. You know, it's arguable, but in the example that I gave you with income level, arguably, if we take the average of income level in Australia, we're going to wind up with something that doesn't really represent the typical score, because those big scorers at the top level of income, who are earning, you know, maybe 50 times more than other people, those big scorers are going to influence the mean and drag it up so that it will give an inflated view of, you know, the average or typical income level in Australia. So in situations like that, we may actually want to consider using a different measure of central tendency, and that's usually going to be the median, what we call the median, which is the midpoint of the distribution. So the median differs from the mean primarily because the median only takes into account the ranking of scores. It doesn't take into account the actual score values. So if we're talking about income levels, for example, those big figures for the higher income level earning members of our society, the actual amount that they're earning is not going to figure in the median. All we're going to do is rank everybody in terms of, you know, their earnings, and then we're just going to take the midpoint of that distribution to represent what is typical, right, in terms of income levels in Australia. So the median actually escapes some of the problems of the mean getting dragged by skewed distributions because it actually doesn't take those score values into account. The mode is actually the simplest measure of central tendency available. And for that actual reason, it doesn't tend to get used very much. It can be useful in some very simplistic situations. So say, for example, when we just want to know, like, you know, which of particular statistical packages, for example, are most popular, we might actually find that the mode, which is just the simplest, just the most frequently occurring scores within our set of scores, you know, is that might actually be applicable in that situation. But in actual fact, the mode is very rarely used in quantitative analysis. So, but it can actually be used in simple situations like just picking, you know, which one of these is nominated most frequently by a group of people in terms of popularity or something of that kind. Okay, so now we've talked about central tendency, and the goal of getting a central tendency index, as I've mooted before, is to get some indication of a typical kind of score within a group of scores, okay? But as we've also talked about, you know, the extent to which a central tendency index, like the mean, actually represents what is typical in a group of scores can vary depending on how spread out the scores are from that so-called typical score. So in order to get an index, so we need to accompany, I suppose, our typical score with an indication or index of how spread out the scores are, from that so-called typical score. So in order to do that, we generate now an index of what we call dispersion or spread, you know, in other words. So the simplest index of spread or dispersion is the range, which is basically just the highest score minus the lowest score, you know, basically indicating what is the actual observed score values that we have in our set. This is a very limited index because it doesn't tell you anything about what's going on in between those highest and lowest scores. So, you know, and once again, in general, we don't tend to use the range as a measure of dispersion. The range can be useful sometimes, you know, generating that in SPSS, for example, can be useful primarily to indicate miscodings in your data, because you can sometimes see that, you know, when you get a very big range, you know, the score values that you actually have recorded fall outside of the actual possible score values that, you know, of the responses that you've got, in which case it indicates that you've got a miscoding. But the range, by and large, is only really useful in that context. Most of the measures of dispersion that we compute in quantitative analysis are based on what we call the variance indicator. So what do we mean when we talk about the variance of scores? We compute the variance of scores by basically getting the differences between all of the scores in our group and the mean. We square those figures, and then we add them all up and divide those by 1 less than the sample size. What on earth am I talking about with that? So let's just sort of decompose that or deconstruct that, so that we get a better grasp of what's going on there. So in order to get the variance, the first thing I'm going to do is take every score value in my group, and I'm going to take the difference between that score value and the mean, right? Now, so what that's going to do, in actual fact, one of the definitions or one of the definitional properties of the mean is that negative and positive scores around the mean are going to balance each other out. So if I do that, I take every score, I take the distance between or the deviation of that score of each of the scores and the mean, and I add them up, they're going to wind up being 0 every time. Not very useful because it's always the same. So basically what I'm going to do now is square that result. I take the difference between every score in my group and the mean, and I square it to get rid of the negative, right? So by squaring it, I'm going to get rid of the negative, because 2 negatives multiplied together is, produces a positive score. So after I've done that squaring, what I have is what we call a sum of squared differences between my scores in my group and my average or mean score, right? Sum of squared differences, right? So that's what I've got to start with. If I now divide that by the number that I have, -1, and I'm going to come back to that in just a second, -1. But if I divide that basically by the n, the number of scores that I have, what do I now wind up with? I wind up with an average squared differences of my scores from my mean, which basically tells me, how much in squared terms scores tended to differ on average from my so-called typical score or mean score. The reason that I divide by n-1 rather than n is basically, it's probably a bit beyond the scope of this unit, but when I divide by n, what that will then produce is what we call a biased estimator. That means that as my sample size grows, my indicator of variance or my value of variance doesn't become closer and closer to the population mean. The reason for that is that I have some restrictions in my data because I'm computing the variance. I am using the mean in order to do that. So that then fixes one of the score values, right, in my group, which is now what we call no longer free to vary. I'm going to be going into this, into degrees of freedom in a little bit more detail in another session, but suffice it to say that basically n-1 is really, just to make sure that we don't create a biased estimator because of our computation, because of the way in which we're computing the sample variance, right? But for all intents and purposes, conceptually, the variance is supposed to represent the average squared deviations of scores in my set from my mean score. All right. Now, this is not overly useful interpretively, because basically we're now talking in squared deviation terms and so on and so forth. So, but if we now take the positive square root of the variance, which we computed earlier on, this produces what we call the standard deviation, and that expresses dispersion or spread around our mean point in the original scale of the data, right? So basically, instead of talking now about, we take the square root, instead of talking about average squared deviations around my mean point, I can now talk in terms of average deviations around my mean point. So you can see that the standard deviation is quite useful interpretively, because I now have, in my mean or median, I now have an indicator of the typical kind of score that I got in my distribution or group of scores. And I also now, with the standard deviation, I now have how much on average the scores in my group or set differed from that so-called typical score. Typical score and how much on average my scores in my set differed from that so-called typical score. So you can see that that would actually be quite a useful indicator of how of the characteristics of my distribution in terms of typicality, but then also how far out, how dispersed my actual responses were from that so-called typical sort of point. Okay, so now that we've covered those, we can actually now start talking about, how different specific score values stood in relationship to the scores of the group as a whole. All right, so any kind of norm reference test will actually give you back what we call an index of relative standing rather than raw scores. And part of the reason is that the raw score doesn't give us much information in terms of where that particular score was with respect to other scores within the group. Was it atypical? Was it typical? Was it what? The raw score doesn't really give you any of that information. In order to get that information, we need to convert our raw score into what we call an index of relative standing, or a derived score, right? It's alternatively called a derived score, right? The most common derived score that we talk about in education is something that should be familiar to you, which is a percentile. And that expresses where a particular score, stood in relation to a set of scores based on the percentage of scores that fell below that given score. So say, for example, if I have a score of 4 and that fell at the 20th percentile, that would indicate that 20% of all scores in my group of scores fell below 4. Right, so a percentile is actually quite good for communicating, relative performance to people like parents and students, because it's quite easy to comprehend. It's quite easy to sort of convey the meaning of that. So they are a bit limited, though, in some situations, and I've given one of those situations in the table on your PowerPoint there. So I've taken 5 students, Andrew, Betty, Paul, Fran, and Oscar, who did 2 different tasks. Okay, so task 1, task 2, and I've actually given you also the scores that they achieved in those 2 tasks. Now, you can see from this very simple demonstration that Andrew would get the same percentile rank in both of those tasks, right? Because he actually was the highest scorer out of 5 in both of those tasks. But if you look into the actual scores that were earned by the students, you can see that in task 1, Andrew's performance was not quite as impressive as it was in task 2, because Betty, Paul, Fran, and Oscar, their scores are actually quite similar to Andrew's in task 1. Their scores in task 2, though, were very different from Andrew's scores. So, in a sense, Andrew's performance in task 2 was actually a bit more impressive relative to other people's in task 2 than in task 1. So percentiles, if we use percentiles, we lose that kind of level of detail, by using the percentile. A Z-score, on the other hand, does take into account the distance between the points in your data or the actual score values that you get. So when we compute a Z-score, what we do is we use both the mean and the standard deviation that we talked about earlier on. So remembering that the mean is supposed to represent a typical score within the distribution, and the standard deviation tells you how much on average the scores in your set differed from that so-called typical score. So the Z-scores use both of those products to indicate where a particular score stood in relation to other scores in your data set. So we use the formula Z equals X minus X bar divided by S in order to compute a Z-score in any situation. So, what does this mean? Basically, what the Z-score computation means is that we will take any score that we're interested in, which will be X. We subtract from that score the mean, right, the so-called typical score within the distribution, right? So what we've got there already is a difference between that raw score minus the mean, right, that we got, and that gives us a difference between, a deviation of that score, against the mean. It can be negative or positive, with the negative indicating you're below the mean, positive indicating you're above the mean. So just in that numerator of that formula there, we have, basically a different score. If we now take that different score, right, where that particular raw score is relative to the mean, and we divide it by the standard deviation, what that actually now does is it converts that score, the difference between that score and the mean, into standard deviation units. It expresses the difference that we can see in the numerator there in standard deviation units. Why would we want to do this? If we recall that the standard deviation represents how much on average score values in our group differed from the mean, this can actually tell us not only whether or not our raw score was above or below the mean, but also whether or not it fell within the average range or outside of the average range. So in the next slide, I'll talk about intelligence tests, and basically every norm reference test that you take is pretty much, gives you back a result, an intelligence quotient that is actually based on a Z-score. So why do we want to convert to standard deviation units? Because we have an indication of a typical score, then we have an average, degree to which scores in our set differed from that so-called typical score. If we now express the relative standing of any given raw score in terms of standard deviation units, we can then see, did the score fall above or below the mean? That is it negative or positive? But also, did it fall more than one standard deviation? Okay, because one standard deviation represents how much on average, the average deviation from the mean. If we get a standard deviation, if we get a Z-score, that falls more than one standard deviation, either below or above the mean, it will tell you whether or not that score is actually beyond the average range of score deviations from the mean. So it tells you that score is atypical. So it's quite a useful indicator of the Z-score. So basically, I've just summarized, I've probably jumped the gun a bit by talking about that, overly excited or something like that there, in terms of slides. So basically, I've already gone about the standard deviation units, but let's just take an example here, right? So if we actually convert all of the scores in a group to Z-scores, we always wind up with a distribution in which the mean is 0 and standard deviation is 1, right? So the average range is always going to fall plus or minus one standard deviation from the mean. So if I get a Z-score, if I convert all of my scores in a group to Z-scores, and somebody winds up getting a Z-score of +2, that means that person was not only above the mean, right? That person's score was not only above the mean because it's positive, but also it was 2 standard deviations above the mean. So that indicates that score is very atypical. If I have somebody else who gets a Z-score of -0.5, that indicates that although this person was actually below the mean, as in the negative, indicated by the negative, they're still within the average range because their Z-score was only 0.5, right? So basically, even though they're below the mean, they're below the average, they're still within the average range, right, of scorers. So converting to Z-scores can actually be quite useful for interpretive purposes. As I mentioned previously, any derived score from a norm reference test usually is going to be some kind of Z-score, a converted Z-score. Underneath them all, they're actually telling you the same information. So I took an example of intelligence quotients that you get back from taking an intelligence test. The kind of intelligence quotients that you get back are actually Z-scores, but they've been basically scaled because, as we've just mentioned, Z-scores come in both positive and negative, and they're actually going to balance one another out in terms of positive and negative. So if we don't want to be reporting back negative intelligence quotients, what we actually can do is basically pick up our distribution and push it, right? We just pick it up and we push it up, we scale it up, so that instead of having a mean of 0, we now have a mean of 100. And we can also fix the standard deviations to make sure that no scores, no matter how extreme they are, run into the negative sort of region. So we would normally fix in an intelligence test a standard deviation of 20. So basically, instead of a Z-score distribution of, that centers around 0 as the mean, standard deviation of 1, we just now have a Z-score distribution that is centered around 100 and has a standard deviation of 20. Tells you exactly the same kind of information as, as a normal Z-score would do. So if I have, for example, a score of 125, based on distribution of 100 with a mean of 100, standard deviation of 20, I get a score of 125. Basically, all this tells me is that not only am I above the mean because it's positive, but also I fall just beyond the normal range, which is between 100 and 120. So they're very useful for interpreting sort of relative standing of scores within a distribution. Okay, so in the next bit of this presentation, we're going to be getting started with SPSS. So I'll be telling you how to read in data. from Excel into SPSS, and we're also going to be using SPSS to generate some frequency distribution graphs, descriptive statistic, and I'll also show you how to generate indices of relative standing based on your SPSS program, which make life a lot more simple when it comes to doing your computations. So for this next bit of it, I'll be switching over to the SPSS window so that you can actually see what I'm doing while I'm going through the analyses. Hey everybody, so what I've actually done here is I've killed the video on your screen just so that we can focus in on what's going on with using SPSS here, and just so that you can, so that I don't have to have a bunch of people watching me sweat when things don't function correctly on SPSS. So you're getting a really raw demonstration of how to use SPSS. Now, one of the first things I'm going to say is, probably, or one of the questions that you might have is, why don't I just, enter the data straight into SPSS rather than, giving it to you or generating it in Excel and then importing it into SPSS? Okay, so the first thing that I'm going to say is basically that I do think that Excel is preferable for doing basic data management. I find it preferable. I mean, not everybody will, but I actually do find it preferable for dealing with data because you can manipulate them easily, move the variables around and stuff like that. SPSS is a bit more clunky for doing that kind of thing. So that's the reason why I've given you all, data in an Excel format rather than SPSS format to start with. So the first thing, obviously, you want to do is basically to obviously open up your downloaded trial version of SPSS. Now, I've actually downloaded that myself to use this, for this demonstration, just to make sure that we're operating with the same version of SPSS. They don't differ terribly much, oftentimes in versions, so they're often not upgraded very much, but sometimes they look a little different. So it's best that we use the same version if possible. Okay, so now that we've opened up our SPSS, let's now read in our file, our data file that we have, generated from our research. Okay, so what we need to do in order to do that is to go to File, okay? And once we've gone to File, we can actually use either the Open or the Import command now. From there. So in actual fact, you can actually open Excel files directly. At one stage in time, you had to import the data. They often went wrong, in the import process and so on. But nowadays, SPSS is actually a fair bit better at recognizing things like Excel spreadsheets. So you can actually open it directly. So let's do the open option to start with. All right. So if we go from open to data, okay, and whoops, it's open to something in my Dropbox. So I'm going to go to my desktop instead. So we can see here that, we've got, it allows us to see what's on our desktop there. And basically, there'll be nothing showing initially because it's looking for SPSS statistics files, or that's star.sav files or star zsav files. So if we now change that to an Excel spreadsheet, okay, oops, and I'm not in the right folder, so that's no good either. I can go into my folder here, which has got my Excel spreadsheet here, and you can see that now the Excel spreadsheet is showing up. So I'm going to click that, I'm going to open it, and it's going to take forever to open. Why is it taking so long? I don't know. Seems to have hung on me. So I've now managed to hang the program. No, it's back again, right? Okay, that's good. Okay, so as you can see, the first dialog box that you're going to get here is basically showing you the data. You can see that in that little preview window there, it's showing you the data. Now, generally speaking, as I say, SPSS is pretty decent now at being able to recognize Excel spreadsheets. So you should see that it's actually coming out like that. If it looks all funny, you might want to go back and have a look at your Excel spreadsheet and see why SPSS is not reading the Excel spreadsheet correctly. But by and large, it's going to be pretty good at picking up your variables there. So we can see here that, the sheet looks around about the same. So we're going to go ahead and click OK there. Okay, so once we've done that, probably the first thing we want to do is save, right? So even though we've got the Excel spreadsheet saved, we're going to want to basically make sure that we actually keep the SPSS data file, because we're going to be doing some manipulations on the data within that file. So in order to do that, we go to File again in the corner there, and we go to the Save As command, right there. All right, so I'm going to save it in the same folder. You can save it wherever you want by clicking in the look in at the top there, and I'm just going to save it as demo.sav. Oh, I actually don't need the SAV because I'll add it there. So I do a save there. All right, so now that I've got my data saved, I can keep coming back to it for all of the other analyses that we're going to be doing in the unit. So, all right, so the first thing that I actually want to do when I've read in my data is if I've got any categorical variables, and you can see here where I've got teaching mode, enjoyed maths at school, yes or no. So teaching mode is my, online, in-person and blended formats. I have enjoyed maths at school, yes or no. And I also have my, did you do a prior statistics course, yes or no, as categorical variables. So basically, even though I put in 1s and 2s to indicate which category they fell into with those variables, it really doesn't indicate anything in terms of them, one being higher than the other. They're categorical or nominal variables there. So, okay, what I want to do basically is tell SPSS, because it doesn't know what a 1 is, a 2 is, or a 3 is, in these data. I'm going to note, we don't have to do this. And, oftentimes I must admit that I don't, but it's going to make life a lot easier if you actually do label these within SPSS, because then when you get your printouts, there's no going back and saying, hold on, what was 1 and what was 2 for you, because it's already labeled within the SPSS file. So what we're going to do is, you can see here, we can go from, in my screen here, you can go from a data view or a variable view. And what I'm going to do here is go to the variable view, and you can see that basically flicks around the data file to show you the variable names on the left-hand side, and then things like the label and so on and so forth on the right. So in order to label, the different levels of our categorical variables, we click the values, right, to the right of that. So if you go here, teaching mode, you can see here teaching mode, right, is on the left-hand side here. We go to values and we click where it says none, right? And what it does, I'll do that again. What it does is it gives you, it opens it up here, and it gives you a drop down here, which you can now open, all right? We can now open it up, right? So what we then do in this is we can open it up and we can put in our values, right, against a label that will tell you what that corresponds to. So the first one in our teaching mode variable is the online option, which is a value of 1. We can now put in the next one, which is the in-person, and then we can put in another one, which is number 3. That's our blended delivery option there. And then we can click OK. So you can see here in the values now that our labels are already imported, and that means we don't have to keep asking questions like, what was the 1, what was the 2, what was the 3, and so on, as I often find myself doing. Okay, so the next categorical variable we have in the set is our enjoyed maths variable, which is basically indicating, did they enjoy doing maths at high school, yes or no? Okay, so again, here, we click the add on there. A 1 is no, I didn't enjoy it. Add again. A 2 is a yes, I did enjoy it, and we click OK. The third categorical variable here is, have you done a prior statistics course? And again, we have a 1 is a no. We have another one, 2 is yes, I did. There, and we OK. So now we've actually got nicely labeled values. Okay, we don't need to label all the other ones because they're basically just on a scale, and there are no categorical values that we can add there. So we can now go back to our data view and see, and look at our data in sort of a more natural format. Okay, so one of the questions that we have, that you have in your assignment is, tell us whether or not people seem to generally have a positive attitude towards learning statistics or not. Now, I'm not going to use that variable because obviously that's your assignment, but I am going to use another variable in the set and do exactly the same kind of analysis that I would be expecting you to do for the assignment in this demonstration. So I'm going to use, instead of that, motivation to learn statistics. And all of the steps that we're actually going through are actually in your class notes in the screenshots. This is basically just a kind of more of a let's say an animated demonstration of how to generate the outputs that you need for your assignment. Okay, so to do any analysis in SPSS, what we do is we go to the analyze command here, analyze, right? So we click the analyze at the top there. And there are multiple ways of generating descriptive statistics in SPSS, right? There are loads of different ways that we can do that. One of the ways is, or one of the main ways is to use the descriptive command, descriptive statistics command. And once you'll find that once you go down to that, you've got a list of options here, and many of these different options will actually allow you to generate descriptive statistics. So the first one I'm going to try is frequencies here. So I'm going to go to the frequencies command here, and I'm going to select our variable of interest, which is motivation to learn statistics, right? So what we do is we've got a list down the side here. We actually click the one that we're interested in, which is here, and we then transport it into the variables box over there to indicate that out of the list of variables that we have, this is the one we want to focus on, okay, here. Now, in this case, I'm going to untick display frequency tables. And the reason I'm going to do that is basically because we've got so many possible score values. Because we measured this thing, you know, and on a visual analog scale, and people could put anything like up to, you know, decimals and so on within there. We've got a lot of different score values that we could actually have. So the frequency table is going to be huge, and it won't really tell me that much because, you know, the differences between the score values can be to the second decimal place. So I'm going to untick the frequencies, display frequency tables, and I'm instead going to just go for charts here. But first of all, I'm going to go to the statistics option here to indicate what I want generated within this analysis. So I click the statistics box here, and you can see it's all blanked out here, but I'm going to want to see a few things when I actually get my output. So what I'm going to do is I'm first of all going to get my measures of central tendency, which is the mean, the mode, and the median. I'm not going to worry about a sum because that's, you know, not of much value interpretively. And I'm also going to get, you'll recognize these terms here, characteristics of my distribution, which are the skewness and the kurtosis of my distribution. I'm also going to get measures of dispersion, like the standard deviation. And I'm not going to worry too much about the range and so on and so forth, because they are, you know, of less value in terms of, you know, interpreting what I have. So I'm going to continue that. I'm also going to now go to charts here, and I'm going to tell it, look, I want a histogram, which tells me the frequency distribution that I have in terms of my group of scores here. And I'm also going to tick show normal curve on the histogram so I can compare my distribution to a standard normal distribution, right? And that will tell me how normally distributed my scores are. I'm not going to worry about the format style or Bootstrap because they, you know, aren't typically used. So if I now click OK, it after a little bit of time, it comes up with my output window here. So it automatically goes to the output window whenever you do any analysis. And you can see here that I've actually got a table here, which gives me a whole bunch of useful information, and also a graph as well, a histogram. So first of all, let's have a look at this table. So you can see here that I've got a mean here of 5.19 rounded to the second decimal place, a median of 5.25, and a mode which is kind of completely out there because I've got multiple modes existing. So by and large, you can ignore the mode that you get because, as I've said, it's not terribly useful. It's even less useful in a situation like this when we've got, you know, score values that differ by like the second decimal place. So mode, forget about it for the moment. You can see also here, though, that the median and the mean are actually roughly the same. In terms of if you're trying to get a bell-shaped distribution, that can be quite a good sign because it tends to indicate that, your distribution is more or less bell-shaped. We also have a standard deviation of 1.85. So basically we have a typical score of, if you look at the mean, 5.19. And we also have an indicator of how much the scores in our distributional group differed from that so-called typical score or the mean on average. So we can say that the typical score was 5.19, but on average, the scores in the group as a whole differed from that so-called typical score by 1.85. Now, we also have here a measure of skewness and also a measure of kurtosis and what we call standard errors associated with those statistics, all right, with those products. So the skewness, the standard error of the skewness, kurtosis, standard error of the kurtosis. That is an important point to take into account here, because when we come to doing our inferential statistics, we're going to have to report on the skewness and kurtosis of our distribution, and we actually use an index in each case to do that by dividing the skewness, or dividing the statistic, the product, by its respective standard error. All right, so in order to get the index of skewness, in this case, I would divide 0.101 by 0.157 to give me my indicator of whether or not the data are skewed or otherwise. I would do the same thing for kurtosis, negative 0.358 divided by 0.313. And what that actually does, and I'll talk about that in a bit more in another session, it converts the skewness and kurtosis coefficients to basically a Z-score format, right? So I can actually interpret the product of dividing skewness by the standard error of skewness. I can convert that interpret that more or less like a Z-score, so that if I do get something that, say, for example, plus or minus 2, that will indicate to me that I have a very skewed distribution, and therefore I might have to, rethink my plan in terms of analysing my data in particular ways. All right, so enough of that. Okay, so we also, as you can see, have a histogram here. And, that shows me basically the actual scores that I get, which is in the bars, and it has superimposed, right, a normal distribution over the top. Now, the distribution is rough, okay? Most empirical distributions, except for very well-established sort of norm reference tests, are going to be a bit rough. But as we can see from this graph, it is more or less normal. It's not skewed, it's not flat, it's not peaked, it's not anything. It more or less complies with a standard normal distribution. So we can be quite encouraged by that basically we have, a relatively normal distribution, even though we've got some, a few funny score points where basically there was a higher frequency than we would otherwise have expected. But generally speaking, this represents a fairly normal distribution, right? Normally distributed list of scores. Okay, what I'm going to do now is I'm just going to get rid of all of that output, and I'm going to show you a couple of the other ways of getting, descriptive statistics using this dialog box. So you can actually get the same kind of outputs by using the descriptive statistics, then the descriptive command itself. And I'm going to do that just to show you that basically you can get pretty much the same output from both of them. So after we enter our variable there, which is motivation to learn statistics, I now go to the options box, and you can see that many of these sort of options are actually pre-ticked. I can also tick the distribution boxes there, which show me the kurtosis and skewness. And what you will see is in the outputs that these actually give you exactly the same information as what we got previously. So the one advantage of using the descriptives command itself is that I can do something fun here, which is that I can actually say standardized values as variables. Standardized values represents or refers to Z-scores. So actually, rather than sitting down and sweating all kinds of bullets, doing manual computations, SPSS can actually give you Z-scores for every score in your distribution all at once, just by ticking that box. So I'm going to tick that box now, just to show you, what happens when you use descriptives and you generate Z-scores through those. So, okay, I'm going to hit the OK button there, and it's taking forever to do this. But anyway, we shall wait. Come along, come along, come along. No? Okay, wow, this is slow. I don't know why this is running so slowly, but anyway, I'm in the midst of it now, so I'm just going to have to make do. Looks like I've actually hung it, basically. Quickly. My apologies for the slowness of this. Why? Okay, I'm going to go while we're waiting for the outputs to show up. I am going to now show you what happens when we use the descriptive statistics command and we tick that box saying show standardized values. What it will actually do is when we go to our data, it's actually added another variable here, which represents the Z-scores of the variable of interest, right? Against every score that, you know, for every individual there. So we can see from this that basically we have for a score of 6.50. 6.50 has a Z-score of 0.71 rounded to 2 decimal places. So that indicates that that person who got 6.50 is not only above the mean, but is actually within the average range above the mean, right? So that person basically, if we define the average range as plus or minus 1 standard deviation from the mean, this person did score above the mean, but you know, it was still within the average range. This person, the second person we're looking at on the other hand, right, who had a raw score of 2.05, actually scored below the mean. You can see here negative 1.69 rounded to 2 decimal places. Negative indicates that they're below the mean, and they got a Z-score of 1.69, which means that they're outside the normal range, right? It's 1.69 standard deviations below the mean. So that person was quite a low scorer in comparison to other people, you know, in the score group. Okay, I'm going to now go back and hopefully I've got my output. No, I don't have my output. Why? Dearie me. All right, let's go again. As you can see, this is actually a raw demonstration, absolute raw demonstration here of you know, what happens when we're using SPSS. Can I get my outputs here? No, I'm gonna, okay. This is it has actually reported glitches to me, so I am going to get rid of that altogether and see if I can rerun it again. So you're getting a real demonstration of, you know, of what it's like to use SPSS. So let me just see if I can actually get it to generate my outputs now here. Okay, I am going to, no, it's not giving me my outputs. That's ridiculous. Okay, so why is it not doing this? All right. No, for some reason, it's not giving me my output file at the moment. So what I'm going to do is pause the video and I'm going to come back after I've rebooted SPSS. So welcome to this very realistic demonstration of some of the problems that you might encounter in using this program. I'll be back in just a sec. Alrighty, so, and we're back. Basically, what I did while I was gone is restart SPSS. Yeah, as I say, yeah, I think it's a useful demonstration because this particular version of SPSS that I've downloaded is obviously suffering a few glitches there. So if you do encounter something like that, just basically restart SPSS and it should come good. So, okay, so I'm going to show you now the second option for generating you know, descriptive statistics and so on here once again. And basically, I'm going to go back to, in order to do that, I'm going to go back to Analyze Descriptives, right? Oops, here. And go back to Descriptives, and it saved my dialog box, which is good. Okay, so I had ticked, as I talked about it earlier on, save standardized values as variables. We saw that before. And I'm now going to tick the options box just to make sure that everything I want is actually there. No, I want kurtosis and skewness. Continue that and click OK. And howdy doody, I've actually managed to get an output window there. So we talked about the Z-scores that it puts into the data file for you earlier on. And now I also have, hush my mouth, an actual output here. And that, you can see, gives you exactly the same figures as we saw before, right? So we have the same mean, got the minimum, we've got the maximum, same mean, 5.19. We've got the standard deviation statistic, 1.85, same skewness, same kurtosis. So basically the difference between this descriptors command and the other one that we use, which was the frequencies one, is pretty much that you can get Z scores out of the descriptors command. So let's give this a try. I'm going to now try to generate the third option, descriptive statistics, using the third option, which is the explore subcommand here. So click explore here. And once again, we can actually pick the variable that we're interested in out of that list, put that in here. But the advantage of explore now is that we can actually divide up our sample by a factor, right, which is called a factor, right? We have a factor list here. So if we want to actually look at not the full sample, but look at, means and standard deviations based on, one of our categorical variables, like whether or not you did a statistics course previously or not, we can actually enter that into the factor list, and that will then give you divided up sort of outputs, for your means and so on and so forth. So let's actually do that just for the sake of exercise here. So we go to statistics, we've got descriptives here, pretty much got everything that we want there. So I'm going to just continue that. I'm going to go to my options, right? And, look at how we're going to exclude cases. Basically, what this is saying is that if you've got any missing data, we're going to take out the case. Listwise means we take out the case. If we do it pairwise, it means that you're only going to take out those variables that, where there are missing data. I'm also going to go to plots here. And under plots, I am not a huge fan of stem and leaf plots, right? So I'm going to untick that. I prefer histograms. All right, to look at. So I'm going to tick the histogram rather than the stem and leaf plot. And I'm going to leave the normality plot with test for a later time. Okay, I'm going to click OK. And my goodness me, okay, so it's actually generated at this time. All right, so you can see here we've got a lot more information, but that is because we are dividing it up between prior statistics course, and obviously this data file didn't save my labels, so I'm going to have to go back and do that again because it crashed. Prior statistics course 1, which means no, I didn't do one, and 2 means yes, I did do one. I have done one previously, and it's now divided up my descriptive statistics into those groups, right? So you have specific now outputs for your different groups defined by the factor that you actually put in there. And it's also given me different distributions for those two groups of people. So prior statistics equals 1 means basically that no, I haven't done a prior statistics course. Equals 2 means that I did do a prior statistics course. So you can now actually compare those distributions because you've actually got, divided up. You've got your outputs divided up by that so-called factor. And so those are the 3 approaches for generating descriptive statistics that we can do in SPSS. So let's now get rid of all of this because we don't need things divided up to answer our assignment question. Let's go into descriptors again, and let's just generate that again. So in order to answer the question that I have posed to you for your assignment data, we have to look at the mean and compare that to the total range of the scores that we could actually get, all right? So you'll remember that we had a score range basically from 1 to 10, for our variable motivation to learn statistics, and we have a mean now of 5.19. So pretty much this is indicating to us that basically, motivation to learn statistics was pretty well spread out. Basically, there was no yes, I hate it for everybody, or no, I don't hate it for everybody, or I'm not motivated, or yes, I am very motivated. We pretty much can see that some people were highly motivated, some people weren't. So it was pretty evenly distributed. So the thing is that we can't really say, by and large, for everybody, because basically they were pretty spread out. So that would be the answer that I'm going to give when I come to the write-up. And I've given you an example write-up in your class notes. So you can actually see how I've gone ahead and interpreted that outcome in your class notes. Well, I hope you've enjoyed this rather, fraught demonstration of how to use SPSS to generate descriptive statistics when you get a group of data. And so in the next session, we'll be talking about using SPSS to do correlations, but first of all, talking about what correlations and simple linear regression are. Thank you for listening.